Hey everyone, and welcome to this explainer. Today, we are literally decoding reality itself. We're going on a journey from the incredibly microscopic tools that scientists use to measure the world, all the way up to the massive macroscopic laws that govern how everything, and I mean everything, moves through space. I absolutely love unpacking these foundational concepts because honestly, they describe every single thing happening around us right this very second. So let's dive right in.
But before we can even begin to talk about, cars speeding down a highway or the Earth rotating on its axis, we have to tackle this foundational question. How do we accurately measure reality? Because to understand motion, we've got to first agree on exactly how we quantify the physical world. Simply put, if we can't measure it, we can't understand it.
So here is our roadmap for today. We'll start with the bedrock, the fundamentals of measurement, then look at precision tools and density. From there, we'll tackle distance versus displacement, map out the 5 types of motion, break down speed, uniformity, and time, and finally, we'll decode distance-time graphs. It's a clear, step-by-step climb.
All right, Section 1, the fundamentals of measurement, the language of physics.
It's beautifully simple how the universe operates at its base. There are just 7 fundamental SI units in the International System, but we're going to highlight the big 3 right now: length in meters, mass in kilograms, and time in seconds. Think of these like your independent base Lego bricks. They can't be broken down any further. On the flip side, we have derived units. These are basically just algebraic mashups of those fundamental blocks. Take force, for instance. It's measured in newtons, but a newton is actually just kilograms times meters per second squared. You're literally just mixing and matching the basics to describe a more complex reality.
Moving into Section 2, precision tools and density. Let's measure the micro. Okay, so what if you need to measure something really tiny? A standard desk ruler just is not going to cut it. This is where the brilliant mechanics of a vernier caliper come into play. It has these outside jaws to firmly hold an object, a main scale marked in plain old millimeters, and this incredibly clever little sliding scale called the vernier scale. The magic trick here is that 10 divisions on the sliding vernier scale are equal to exactly 9 millimeters on the main scale. By looking super closely to see exactly which line on the sliding scale perfectly matches a line on the main scale, we can snag measurements down to a tiny fraction of a centimeter. It's genius!
But wait, what if you need to measure the thickness of a single pane of glass or a super thin piece of copper wire? Enter the screw gauge. This tool uses a U-shaped metallic framework and a finely tuned screw thread. By giving the screw complete rotations, a pitch scale combined with a 100-division head scale lets us measure distances correctly to 1/100th of a millimeter. Guys, that is significantly thinner than a single strand of human hair. It's just an astonishing piece of precision engineering.
And when we combine these highly precise measurements of mass and length, we can calculate density, which remember is just mass divided by volume. These tools let us confidently figure out the density of perfect, regular metallic blocks, or liquids, and even weird, irregular everyday items like a small stone. Actually, for a stone, you just drop it in a beaker of water, see exactly how much water it displaces to find its exact volume, and boom, you have your density.
On to Section 3, distance versus displacement. Time to zoom out to the macro.
Picture this. You go for a simple jog. Distance is simply the total ground you covered. If you jog in a giant winding circle around a local park, your distance is the entire perimeter of the path you took. It's always a positive number, and it only cares about the magnitude, the sheer amount of ground covered. Displacement, however, is totally different. It is a straight, direct line drawn from your exact starting point to your exact ending point. It considers both magnitude and direction. So if you finish your jog sitting on the exact same park bench where you started, your displacement is literally 0.
So the absolutely crucial point here is how this difference affects speed. Speed is just distance over time, right? But velocity is displacement per unit of time in a specific direction. If you don't have a specific direction, you just have speed. Velocity is a vector. It absolutely requires you to know exactly where you're going.
Section 4, the 5 types of motion. Let's categorize movement.
Now, physicists love to organize things, and they classify almost all movement into these 5 main buckets: translatory, circulatory, oscillatory, periodic, which is sometimes called repetitive, and random. So let's break down what these actually look like in our everyday lives.
First up, translatory motion. This is when an object displaces from one position to another without any rotation at all. Think of a car driving in a line down a highway, or sliding a textbook straight across a desk.
In contrast, circulatory motion is all about moving in a circular path around a fixed axis. The spinning of a toy top, the rotation of a ceiling fan above your head, or riding a massive Ferris wheel. That is circulatory motion in action.
Then we have oscillatory motion. This is that classic swinging back and forth around a central resting position. Think of the pendulum of a grandfather clock, or the vibrating string of an acoustic guitar. Next is periodic motion, which repeats over highly predictable, specific time intervals, like the steady rhythm of your heartbeat. And finally, random motion. This is totally chaotic and unpredictable. It lacks any sort of specific pattern. A great example? The erratic, fluttering flight of a butterfly through a garden, or invisible gas molecules just ping-ponging around the room you're sitting in right now.
All right, Section 5, Speed, Uniformity, and Time. Calculating pace. Let's look at a really clear, bold calculation. If you're on a road trip and your car covers 120 kilometers in 2 hours, we divide that distance by the time to get a speed of 60 kilometers per hour. This perfectly illustrates the inverse relationship between speed and time. Think about it. If you want to travel that exact same 120 kilometers, but you only have 1 hour to do it, your speed literally has to double to 120 kilometers per hour. Faster speeds always require less time to cover the same amount of ground.
But you know, real life isn't always a smooth ride, is it? Let's compare uniform and non-uniform motion. Uniform motion is perfectly steady and predictable. You are covering equal distances in equal time intervals, like a car locked on cruise control on a totally empty stretch of highway at 2 a.m. Non-uniform motion, though, that is the messy reality for most of us. It's unequal distances covered in equal time, constantly changing speeds, slamming on the brakes, and hitting the gas through heavy, unpredictable city traffic.
And honestly, why does an object maintain uniform motion in the first place? Well, the answer is inertia. Inertia is a foundational property of matter. It essentially means objects are lazy. If an object is resting, it really wants to stay resting. If it's moving at a steady speed, it wants to keep moving at that exact speed forever, unless an external force, like the friction of the road or, a brick wall, forces it to stop.
Okay, final section. Section 6, Decoding Distance-Time Graphs. Visualizing the journey.
One of our sources brilliantly compared reading these graphs to looking at a sports scorecard. With one look, it instantly tells you the whole story of the game. Demystifying these graphs really takes just 3 simple steps. First, look horizontally at the bottom, the x-axis. That almost always represents time. Second, look vertically at the y-axis. That represents the distance covered. Third, and absolutely most importantly, analyze the slope, or the steepness, of the line drawn between them. That slope is the literal visual representation of speed.
With just a single glance, the shape of the line gives away the whole plot. A steeper slope? That means a higher speed. A completely flat, horizontal line? Well, time is passing, but the distance isn't changing at all, so the object is perfectly at rest. A straight diagonal line indicates beautifully uniform, constant speed. But what if you see a curved line? That means the speed is constantly changing. That right there is our non-uniform motion. That's our poor car fighting through rush hour city traffic.
Wow. Okay, so we have gone all the way from the microscopic sliding scales of a vernier caliper to reading the visual stories of macroscopic motion on a graph. Before we wrap up, I want to leave you with a bit of a mind bender to ponder. As you sit here watching this explainer, you probably feel like you're completely at rest, with absolutely zero displacement. But remember, the Earth is displaying circulatory motion around the Sun right now, and our entire solar system is translating through the Milky Way galaxy. So are you ever truly at rest? Think about your own inertia, distance, and displacement in this grand, incredible physical world. Keep learning, keep questioning, and I'll catch you in the next explainer.